Thank you everyone who came tonight. I'm excited to present on the introduction to deep learning, where we're going to go over the basics of neural networks and how deep learning works. To go over our agenda tonight, I'm going to do, at the beginning, a presentation on the fundamentals of deep learning and neural network. And then for the rest of the meeting, we're going to go through a coding exercise with them. So first, what is deep learning? Deep learning is a subset of machine learning, which is a further subset of artificial intelligence. They're not the same thing. You may have heard the terms all used interchangeably, but they all actually mean different things. Artificial intelligence is literally just the idea of trying to make a program that mimics human intelligence. And this is a broad category that includes machine learning, but also includes like symbolic programming, or in some sense, like well-defined algorithms. And it's supposed to be like a program that can like reason and adapt like we can. Machine learning is the subset of that, whose idea is that its performance, its ability to solve tasks will improve with more data over time. It's like the idea of like how we will learn off of information to improve ourselves. Machines will do the same thing. And then deep learning is a further subset of that, where they will take in the data, but feed it through a neural network that help learn the idea of the model, which is a very powerful system compared to other like classical machine learning techniques. Now you might be asking, why do people use deep learning? Well, back in the day, people used to like hand engineer all of their features for whatever kind of program they were trying to make, which would be very time consuming, very fragile in how well it could work, and trying to cover every single edge case for solving a problem just was not scalable. For example, here we can look at like trying to do face detection, trying to detect the face in the image, and you have like all these different features. Like you have low-level features for trying to detect different lines, like detecting like a vertical line or horizontal line. Simple enough, human could write that up. Then they put those together to try and do like middle level features like your nose, your eyes, your ears. Maybe feasible. There's a lot of different variations to how those could look. And then trying to put all those together for every possible scenario of a face by hand. No human can do that. That's going to just take weeks, if not months, if not years. It's just not worth the time to do that. So if humans can't really put all of that together, how can we learn those features to solve our tasks directly from the data itself? The way we do that is with artificial neural networks. Artificial neural networks are inspired by like the neurons in our brains. Like as you can see here, I'm sure you all have had a basic biology, of course. Like a neuron, when it goes, it has like a signal come in, it does some kind of internal biological work inside, and then it does an output, how a brain works. And the idea of that is we take a very simple mathematical version of that operation to build our neural network. And it's all based around the universal approximation theorem, which is a theorem that basically says a neural network there is a neural network out there that can approximate any possible function ever. As long as you have a complex enough model, you could theoretically approximate any function to near exactness. And they're very powerful because compared to other traditional machine learning models, which had like very specific ways of structure, they're very generalizable because they're all built around this single foundation, the perceptron. And the perceptron is a very basic system. It's basically you have a series of inputs, and then you have like a series of weights, you multiply them. So just a linear combination of inputs. Like you would times x1 by weight 1, then plus x2 times weight 2 plus x3 times weight 3. And then you sum them all together, which you then wrap around a non-linear activation function, which you then just set as your output. And this equation is the core of the perceptron and is therefore the core of deep learning. There's no caveat on this. There's also a extra term on top of your input called bias that just helps to adjust like how high or low your output should be in general. You can just treat it as like alongside your inputs, you just have a one appended to the end of it with like a bit of extra weight. But otherwise, it's all the same formatting. It's just your series of inputs, and then your one, all multiplied by your weights to sum together, wrapped around some nonlinearity. Normally, we don't write this in the like sort of summation format. We write this using matrix multiplication, which is shown here. And we generally represent that as like our x being our series of x inputs times our weight matrix, as you can see here, which is just a very simple vector operation, and plus or bias wrapped around our nonlinearity. Now you might be asking, like, what is this activation function I keep talking about? It's basically an idea of trying to just take a linear input, just like a line, and then give it a nonlinear shape. For example, here we have our sigmoid function. And this is basically just a simple function that will take in any input on the bottom and then wraps it around 0 to 1 smoothly. This is very popular in like doing probabilities or something like probability. Like if your value is less than zero, then the probability of your output will be less than 0.5. And if it's greater than 0, it'll be greater than 0.5, right? There's a bunch of different activation functions out there in the world that are popular. There's the sigmoid function, which wraps between 0 and 1. There's the hyperbolic tangent, which is between -1 and 1. And then the rectified linear unit, which is 0 for all values less than 0. And then just linear upwards. They're all differentiable. That's the core thing, is that you can, whatever activation function you use, you can derive with it. And they're all nonlinear. They're not just like a straight line. And below here, you can see some like basic code, how you would write using code using PyTorch, which is a common library for doing neural network viz. And so you're going to be asking about, why do we care about these activation functions? Why do I keep bringing up nonlinearity? The whole point of active function is to implement nonlinearity. And so on the importance of nonlinearity, I want to propose to you this. What if we wanted to build like a neural network that could distinguish like the red and blue point? Like we want to draw some kind of line or curve around the point. Do you think you could just draw a straight line that perfectly splits the red and blue points? Yes? No? No? Okay. Oh, if you just have like a linear activation function, no matter what type of model you implement, it's always going to just have a linear decision no matter what. No matter how big your network is, no matter how fancy you make it, it's always just going to be a straight line. But when you add non-linearity, you can make curves into your model and make curves into your decision. And this allows us to approximate any type of function that is out there, however complex it is. Like here, instead of just having a straight line, we can now draw a curve around the function itself. So let's just go over a very basic example. Let's say we have our bias is W0, and that's just going to be 1. And then we have our two weights of like 3 and -2. If we were going to input that into our function of our W0 plus our inputs times W, that's just going to be x1 times x2 times W. And so we basically just get out 1 plus 3x1 minus 2x2, right? That's just a straight line. It just looks just like a straight line. And that is, it's just pretty much a straight line, but then let's try out an input into it. Let's try like -1, 2. This is going to be on this space. We're going to input it in, and we're going to get through. And then we're passing it through our nonlinear activation function, which here is our sigmoid, the one that wraps between 0 and 1. If it's less than 0, it's less than 0.5. And if it's greater than 0, it's greater than 0.5. And we can see that we get near 0. And so what we can do here is that from our function, we've now defined basically a probability space. We can now say, like, if it's here, we're saying there is less than a 50% likelihood that something's going to happen. And if we wrap it, and if our values are here instead, it will be greater than 0.5. So we've added a probability sense to our equation. Yeah?
Sorry, I think I came late. Can you just go over what is a perceptron?
Yeah, so Yeah, how about I step back for a second? Perceptron is basically just a linear combination of inputs, just like a weighted linear sum wrapped around like some kind of non-linear activation function. Some way of making like the line into like a curve of some kind.
Do you know why it's called perceptron? Perception.
Yes, I think the play on perception, that goes back into whatever puns they were thinking of back in the 1950s when they made this. I don't know. But so,
It's a way of moving like rings.
so there's that group. So I just really want to hammer it into everybody that to remember this whole series of inputs, this sort of like just weighted sum wrapped around some kind of non-linearity is the core of everything. This is exactly what all neural networks are. They're just a bunch of these. And so for the rest of the night, I'm going to be using a sort of simplified diagram version of them, where we're going to just have our inputs going to a Z, which we can just assume that we have our non-linearity and our bias wrapped in there. Like you can see that we have our inputs and our weights. Then internally we have some like bias parameter that we already know. And then we're sending out our Y as an activation function through that Z. Make sense? Great. So let's say we wanted to do multiple outputs. Like we don't want to just do a bunch of inputs to one. And let's do two. That's easy. We have basically for all our inputs, we have our first output that we connect to, and then we have all of our weights connected to that one. And then similarly for our second output, we're going to have all our connections out to that second one. And as you can see in our equation here, like if we had Z1, we're just going to index by I. So it would be Z1 is equal to the bias, of that first node, plus the weights of this first node summed together. And then similar for the second. Since all of these inputs are like so densely connected, like every input goes to every output node here, we call these dense layers because they're densely connected. Because every possible combination here already is existent in the network. So it's like a very dense sort of system. Make sense? Okay, so this is how you would write a dense layer in PyTorch code. I know it looks like a lot of code, but it's honestly rather simple. Like you first just start with initializing the weight and bias of your perceptron node. Like here, you're just saying we're going to have some W's of the number of inputs we have, and then the number of outputs we have. Like we could have 3 inputs to 2 outputs. And then we also have the bias, which is just the number of output nodes we have. So if it was 2, we would have 2 bias. And then when we're passing it through our network, when we pass our inputs through the network, we just multiply our inputs by our weights. Then we add our bias to it. And then we just wrap our non-linearity through it, and then just return the output. Make sense? That's easy enough. So that's how you would do it if you were writing it, having to write out every step manually. Very luckily for us, PyTorch makes it a lot easier than this, where you just have to do like a neural network linear, where you just put in the number of inputs you have. Like here we could have M, and then we have our output feature, just 2. And this makes it vastly more simple to code up. You just have to write the one line. Now let's go a little bit. Let's go, instead of just working from a single, like from just input directly to output, let's go to a single layer of a neural network. And so instead of just having input to output, we're going to have an input, go to a hidden layer, and then go to our final output. And it's called a hidden layer, but we don't directly observe what's going on in the network. We know what we are inputting into the model, and then we know what we are getting out of the model while we're like watching the output and seeing what's going on. But we know what's going on here and what's going on here, but we don't know what goes on here. That's why it's hidden. And these are all still perceptrons. So they're all working the same way. Like here at Z1, we're just going to sum up the weights of the input of like X1, X2, and XM into here, then wrap it around a non-linearity. And then similarly, we're going to do that for all the nodes here. So there'll be some intermediate values. And then once we pass through that layer, we then do the same exact thing with the Y, where we're just going to take in all of our values that are in our hidden layer, multiply them by some weights, sum them together, and then pass them to our output and wrap and run some non-linearity. Does it make sense? Yeah. And these are, like I was said before, and I'll say many times, these are all just perceptrons. These are all just like adding, taking your inputs and then multiplying by weight and then just summing them together.
So just at the very end with those two values, we put them in a linear function.
Mhm.
And then we send them through a non-linear function to get like a complex result.
Yeah, so in a sense, yeah. So like we're gonna have our input here, that's, yeah, pretty much it. We have a linear operation, our linear sum, and then we're passing it through a non-linear operation. And we do that even here with the final outputs. It depends on the model you're using, but usually through all of the hidden layers, we're wrapping them through non-linears. And then when we get to the output, we'll wrap that also through a non-linear, depending on that. And so, because I don't want to show off all of those arrows and make it all look very complex tonight, usually the way we show this architecture is pretty simply with just like the input to the X to our hidden to the X of our output. And so this is just like a single layer of a single hidden layer. And if you wanted to do that in PyTorch code, it's very simple. You just have our linear layer from like X1 to Z1, then wrap it around a non-linear function like ReLU, and then you do our linear function out from a hidden layer to our output. Very simple code.
Oh, but I thought, like every input was being passed, like every, node is in the hidden layer for every neuron.
It is.
Okay.
Yeah, this, so like I would show here, I would have all these arrows here.
Okay.
And I'm showing them, and then I'm just showing a simplified view.
Okay, so then in the code, that's what the linear does.
Yeah, that's what the linear does. It's doing a linear multiplication across all of the input. Yeah. Yeah, it's just a very nice, easy wrapper for all of it. That's the great part of doing it in code, is like all of this complexity is hidden behind a very simple code layer. Now, if you wanted to do a deep neural network, you basically just have a bunch more hidden layers, like showing us these X's here. Like you could have, instead of just one, you could have a bunch before this and then a bunch after this. And you try, and the way you build neural network models is that the more complex your problem is, the more hidden layers you have. So if it's a very basic problem, we might need just like one hidden layer or two. But for something, for example, like image classification, I know those can get to like 30 or 50 layers. And then if you get to LLMs like ChatGPT, those have 64 layers alongside other features inside those models to help even learn even more complexities. But this is a very like high level overview. Does anyone have any questions about this?
So just one series of inputs, n amount of hiddens, and then one final output, basically.
It doesn't have to be one from output. You can have like two nodes of output, but there's generally just like an output.
Okay.
But like it can be depend, like if, for example, if we were trying to classify if an image was a digit, you would need 9 digits. You would need 10 output nodes because you would have 10 digits. You need to figure out the probability if your image you put in is digit 0, digit 1, digit 2, et cetera, et cetera.
So for that same example, how many input nodes would you need?
For that, it would depend on your image.
One for every pixel?
Yeah.
Is that-
That's how you do it. You do it one for every pixel.
Okay, wow, that's a lot.
Yes, it is a lot.
You're basically like, you have an efficient matrix, and then you have to, or like flat in it and put like a column. That's just every fixed, you know.
Exactly. So that's for deep neural networks. And if you wanted to do that in, yeah,
Sorry, is there like a mathematical relationship between the number of neurons in a hidden layer versus the input layer?
not really, no. Not really, because the thing about it is, so the hidden layers, so the thing about it is that the number of hidden nodes you have here in your hidden layer define how many like unique features you're trying to learn here.
Okay.
So like if you only have, like here, if I only had 4, I'm basically telling the model, I'm trying to learn 4 unique things right at this layer from my input. Well, if I have like 1,000, I'm telling the model, I want to learn 1,000 unique different things from the input here.
Okay, gotcha. That makes-
And
So
so,
a lot of times, like usually you would see it has more than that input
Mhm.
and maybe some power of two after that, like you have
Yeah.
like two going in, maybe you have like 4 or 8 in the
Mhm.
middle. Okay.
Yeah.
And that, but that's just to do it makes it just to capture more information.
And so if you want to write it in code again, it's very, very easy. It's just basically just doing a sequential wrapping around like a linear layer to a non-linear, to a linear, to a non-linear, et cetera, to whatever output you want. Yeah,
But all of it is basically the same size or not?
no, they don't have to be the same size. They can be different sizes. Usually they are different sizes. You might have 1 or 2 layers right after each other that are the same size, but you can have whatever size you want. You might see in the future me talk about something called an autoencoder. That's a special type of neural network where basically we have a large input. And then you go to subsequently smaller and smaller inputs, so you get to like a very small layer before expanding out again to bigger and bigger and bigger back to your original size. And so these are all different sizes. So let's do an example problem of a neural network. Let's do an example problem. Are you gonna graduate? Let's just do 2 simple features. The number of classes you failed and your current GPA. Let's say you are a great student, a decent student, I would say a good student, or you've only ever failed 1 class and you have a 3.9 GPA. I don't know if you can actually have a 3.9 GPA if you fail a class, I never really looked. But for sake of the system, let's say, yeah. So we pass those, that's our input in, and let's say we pass through our hidden layers, and then we sum all those out to an output, and it says, you have a 10% chance of passing. Do you think this person has a 10%, only a 10% chance of passing? Yes, no, you think that person's gonna pass?
Yes.
Yeah, that's what it should actually be. So the model was wrong. Why do you think the model was wrong?
Because the weights and biases were random first.
Correct. Right. Yep, we basically just set it up completely randomly. We haven't learned anything about the model. We haven't tried to like, adjust anything. It's just a completely random start. And so it's just basically saying a bunch of random things. And so we need some way to measure how the model is wrong. Like, how can we tell it what it's going to cost it to be wrong? And so that's what we call our loss. And the loss of our network is basically a way of measuring the cost of being wrong. And it's basically just a direct comparison of the model's output compared to the actual result. And so that's for like one single sample. And when we take that across all of our data, all of our inputs that we're going to be trying to learn our model off of, we call this the empirical loss. And it's just measuring the entire loss over the entire data set. This is also called like the objective function, the cost function, the empirical risk. You're also going to see it called the cost function, but it's originally the empirical loss. And so it's sort of the average overall. So we're going to pass in all of these inputs, get all of the model predictions, and then compare them to the model output. And so we wrap this all into an average that we label with JW, because J is our loss function of our currently existing weights. Does that make sense?
Wait, that, the vector, why, that's like the label data, like that's something we already have.
Yeah, that's something you already know. That's the ground truth. That's stuff where we know what that result is already, and that's what we want. We want the model to predict this, and then this is what it's actually predicting. So sometimes it's really wrong, sometimes it's quite right, and sometimes it's like, okay. And so we're measuring with our loss function how wrong the model is at each of these samples. And then we average them together to get like an average sense of how right or wrong our model is.
This slide, like, simply, like, how do you determine if you get the X or the right mark? Is that just like mistake?
So just the sake of explanation. There's no actual networking, you know, I'm just showing off an example. So now we have a loss function, but there's a bunch of different types of loss functions. For example, with regression, there's a 2 popular ones called the mean squared loss and the mean absolute loss, which is basically just measuring either the square of the direct difference between the prediction and the actual value, or it's the absolute value. You've probably seen these before in statistics. They're just very simple systems. And then for classification, we use a different loss called the cross entropy loss. It's a bit more of a complex loss that looks really fancy, but it's basically just measuring the probability of what you outputted it as times the, basically the probability of what your answer should be times the log of the probability of what you actually got. Yeah,
What's the W in this case?
the weights, the model weight. W is all your model weights. But yeah,
So for cross entropy loss, it's the log of the actual answer times the log of,
it's the value, it's the probability of your actual times the log of what you did get out of your model.
okay,
You can remember, F is supposed to represent our model here. It's supposed to be what our model is with our input features and the current weight of our model. And so just remember, the cost function is measuring how wrong our model is based on our current weight inputs. So that's our loss function. This is how we measure loss. And so the big goal of training a neural network is to try and find the network weights that lead to the lowest loss. We're trying to find whatever combination of weights lead to the smallest possible loss for our function as possible. And to do this, we use a system called gradient descent. Now, for gradient descent, it's basically the idea of we have our model weights, and then we have our error, and we have like a landscape of that. Like as you can see here, if we had some weight here that was this value, it's going to have a high loss versus here with our low loss. And the way we do gradient descent is that we first pick some random weights. We start with some random weights that we're trying to learn a model off of, and we measure whatever the current error is with those weights. We then compute the gradient, which is basically just the slope of the loss curve with the error at that point. Basic first derivative. You all take calculus. So once we compute this gradient, we take a small step in the opposite direction. Like as you can see here, we're seeing that we know at this point in the loss, it goes upward. So instead, we're going to go down the opposite direction, but at a small step. And we're going to do this again and again until we find until we find the lowest possible value for our loss. And that leads us to the best possible weights. That make sense?
Yes, but when you say, we take small steps,
Mhm.
what does that really mean in math?
Okay. So basically what that means in actual math is that to show it in like actual code, is that when we start our initialized weights, we're going to compute the gradient and then we're going to update them by subtracting by a small amount of our gradient, which we call the learning rate.
Okay, okay,
And
so
so-
it's just like a scale or like a scalar we multiply?
Yeah, just a scalar multiplier.
Okay,
And then we're gonna do this into over and over and over and over and over again until our model converges. And as you can see here with PyTorch, this is very simple system to use. Like we're just going to set our learning rate and we're going to initialize randomly, and we have some learning rate. And then so for the compute our loss, compute our gradients, we're gonna compute our loss function, compute what the gradients are, and then update the weights by the negative direction of the gradient. And then we just reset the gradient in code because that's how PyTorch works, you have to reset it. Does this make sense? Great. So note, so I was showing before, we're gonna try and do it across all of our data. Usually in machine learning and neural networks, you have like hundreds of thousands of examples. It's a little too time expensive to try and calculate across all of the data each time. So what we do instead is that we just take like a handful of them, what we call a batch, and we just calculate the gradients off of those instead, which doesn't give us as good of a gradient direction as taking in all of the data, but it can give a good approximation while giving us computation benefits. So to compute gradients, it's a little bit of a process, because neural networks have multiple weights. They don't just have one, you have a bunch. So how do you calculate this, a small change? How do you calculate how a change in one weight can affect that final loss function? It's a change. Congratulations, you're back in calculus one. So let's say you want to figure out how does weight 2 affect the value of our cost function. So basically what we're gonna do, delta JW over delta W2. We're gonna see how the change in our loss is affected by the change in W2. And we basically do that by finding how our loss function changes by our prediction value, our prediction node, times the value of our prediction node changing by W2. And this is just basic chain rule. So that's how we would calculate for W2. And so with that, we can now calculate W2. But what if we wanted to calculate W1, one that's like even further behind? It's not, because now it's even more change because you have to jump multiple layers through. So how would you do that again? How could you jump from our cost function all the way back to W1?
Could you use the chain rule again?
Yes, and then use the chain rule again. Dang it, technology. So we can just use the chain rule again, where instead of going from the error to y to just W2, we can go from our error to our y to our z to our W1. And so we're just going to keep going chain back and back and back through, like we're basically propagating from the end of the network to the beginning of the packet. That's back propagation. And we do this for every single weight in the network. And we calculate the gradients for the earlier nodes in the network from the ones later in the network. Does this make sense to you all? So that's that's basically how we calculate the gradient. And this is all handled in code. You don't have to write it. So something you may have been thinking about that I brought up is this learning rate. Like we have our gradients, but we're now adjusting them by some value. How do we define this value? How do we figure out what this value should be? And so this is what we call the learning rate. And there's a few different, and defining the learning rate is a very important thing. Because setting the learning rate basically tells you everything about how your model. But if you set a really small learning rate, then your model is going to take forever to train. Very, 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 very slow. And then you might get stuck on like a plateau or some tiny local bit. Like we got stuck here. We can't train because our learning rate was so small and we can't move. But if our learning rate is too large, then we're going to start overshooting and we're just going to jump around a lot until we shoot up into space. That's not great. That's the exact opposite of what we want to do. Yeah.
Is this the same concept as like momentum?
Momentum in machine learning is something slightly different than. Momentum is, so to give that for momentum is the idea of like if you have a small learning rate, you could still continue moving forward because your learning rate elsewhere was higher previously.
Oh.
So a small learning rate means you will train too slowly, and a high learning rate means you're going to shoot up into the sky. But if you have a good stable learning rate, then you can slowly move until you find the bottom of your loss. And you find the best possible way to score your model. So finding the learning rate is a very important thing to figure out. So how do you set up your learning rate? The first thing, try a bunch of them, figure out what works. This is a very brutal technique of doing it. Still very popular because sometimes people don't want to be fancy, but we can be smarter than that. We can instead try and use a learning rate that can adapt to what our current loss value is. And that can be maybe like bigger or smaller depending on how large the gradients we calculated were, how fast are we training the model, how big our current weights are, etc. Instead of just trying to keep a single value the same the entire time we're learning the model, we can adjust it so that we're not suddenly going to be like having a value that's way too large right at the end of training or way too small at the beginning of training, right? And so for that, there's a bunch of different gradient descent algorithms that we have in code, we have like
Second.
Adam, they have like stochastic gradient descent, Adam, added delta, added grad, or the prop. You can look these up on your own time. They all work in different ways. Adam's very popular. XGD is still very common. They're just all a bunch of different techniques you can use. And then to show it all, like how it's all put together, now that we've gone over this entire process, it's basically just a constant loop of one, feeding in our training data to get predictions from our model, collecting what the loss of the model was compared to what it should be, calculating the gradients of all of our weights in our network from our loss, and then updating our model based on those gradients. We do that, yeah?
Can you explain why we put really gradients in?
So we basically zero the gradients because in PyTorch code, if you don't, then the gradients will start adding upon themselves over and over again through different iterations. It's just, it's wrapper code you have to use in PyTorch to reset the model. Yeah. So this looks generally pretty simple code, right? Just a couple of few lines, you're gonna write those instantly. This is what training a neural network is like. But the thing, when do you think we should stop training? We have it basically going on forever here, but at some point we have to stop, right?
Like when it gets like extremely close or to a desired amount close to the actual value of it.
Yeah, basically like when the loss is minimized.
Maybe you could minimize your loss of your training until it's the dead minimum, but you might not want to. Because there can be problems.
Oh, yeah.
So let's talk about fitting. So there's two types of problems we're going to be having with training all the time. And you're gonna have to try and not let either of these happen. One is underfitting, which is basically when you train for not enough time and your model really hasn't learned the data and how to resolve the problem. Like here we have a curve and it's just predicting a straight line. You did not spend enough time training. But then you can also have the other issue of overfitting, which is when you spent too much time training, you spent forever. And so now your model is really good on your training data, but if you try and feed it on anything else, it's not going to work well. The model did not generalize well to any new data. So that's why you can't just train until your model hits the dead bottom of your loss. Because you can train for all that time and you can get really, really, really good on your training data. But the moment you try and get out of your training data toward anything you've never seen before, you're gonna fall apart. So it's a constant balance of figuring out how long you should train until you get that ideal fit. And a common way of trying to figure out when to stop training is something called early stopping. And early stopping is basically the idea of we stop training the moment we even get a signal that we're going to overfit. And so for that, we sort of have like two sets of data we use. We have our training model, our training data, the model we're going to use to update our gradients and all that. And we're going to call that curve there the training error. But then we also can have what is called a validation set, which is basically data the model has not seen before, but it's still evaluated on to see like how well is the model learning on data it's never seen. Does that make sense? Like you could be studying for an exam, you could take a bunch of practice tests, look at the answer sheet, do it over and over and over and over again to learn that. But then at some point you have to test yourself on the actual exam and see how well you are doing. And you can't look at that answer key for your actual test. You just know if you passed or not. And so we're going to do that. We're going to learn the problem. And eventually we're going to learn. We're getting better at validation, we're getting at training. But then at some point, validation shoots up. So instead, we're going to stop right before validation starts shooting up. So when we get as best as possible on our validation data, that's when we stop training. Does this make sense?
Like, how do you determine where that is? That
Like,
are you like testing your model on like the validation set like after you trained it or while it's training?
Well, it's training. So you remember that training loop where we like passed in our input, made our predictions, adjusted the found the gradients and adjusted it? After we do that, we feed in our validation set and find that loss.
So that's on like each epoch,
Yes, each epoch.
of that picture.
So we're gonna do that over and over. We basically feed that in and we just save the values. And we stop training the moment like the validation set of the current epoch is greater than the previous.
What if it like overfits on the validation data set as well? Or is that like not possible?
That is and isn't possible. So that's a great question that gets into the theory of what validation and testing sets are. The idea is basically you can, for basic terms, you're not overfitting on your validation data from training. Because you're not adjusting your weights on your validation data. You're only adjusting your weights on your training data. That's the whole point of the training data. The training data is what you train on. It's what you use to adjust the weights. The validation data is the test to see are your weights now actually going to be good for anything you've never seen before, or is it now just only going to be good at what it was trained on? Like I said before, the training data is your practice test. You can view the answer key. You can learn how to get from the question to the answer. But then the validation set is the actual final. You don't know what the answer key to the final is. You just know what the final score you got on that is. And so you're going to keep trying to learn the material until you are as good as possible at taking that final exam and not just trying to memorize questions. Yeah. So to just give a final overview of everything we talked about tonight, is that first, the perceptron is the core building block of all of this. It's basically just a linear combination of inputs, just your inputs times some weights, wrapped around some kind of non-linear activation, which there are plenty of them out there, very popular. And we basically stack layers of the perceptrons together to build a neural network. And then we optimize this neural network via backpropagation, where we input our model, get our predictions, measure how well our predictions worked against our actual ground truth, and then we backpropagate through that using backpropagation chain. And then when we're actually training, there's some techniques we're going to use with that, such as using like an adaptive learning rate, training on like batches of our data, and then early stopping once we're starting to see that the data we've never seen before is starting to actually do well. Any questions? No? Sound good? Cool. Let's check out the notebook. Coding time. Does everyone have this open already? So for the first things first, we're just going to make our own copies of this. But we don't want to write it onto ours. We're going to have our own. And so cool. So everyone should have this. Then you're going to want to go up here to connect. Make sure it says connect with a GPU. Like make sure it's like a T4 runtime. It should already default to that, but just make sure it is. And so then we just have that saved. And so let me zoom in.
How do you make your own again? What do you press? Or do you just click connect GPU?
File, save a copy and drive. Did you already do this? Make a copy and drive?
No, okay.
Yeah, you just make a copy and drive first. And make sure you connect. If you also start running the code, it will also connect automatically. So this is our intro to deep learning slide. So first I'm going to first talk through our code. If you were here for our previous workshop, you may have already seen these libraries before of like NumPy, Pandas, and Matplotlib. NumPy is for array operation, Pandas is for like data management, and Matplotlib is for plotting. Tonight, we're going to be using a different library, PyTorch. PyTorch is the library that neural networks are built in. You might hear about another library called TensorFlow. That's sort of popular, but it's nowhere near as used as much as PyTorch is. PyTorch is the library everything's used in. And tonight we're going to be showing off a few different functions of it, mainly the base library, The neural network layer that you remember from the presentation, our activation functions, the inputs, the data loader, which let us manage our data, and then our optimizers like the SGD, the Atom, etc. And then we also have Torch Vision, which is good for image data, which we will be working with tonight. So the first thing you're definitely going to do is just press the play. Is that what the code run? And then it should be finished the moment you see the check mark. Next, we are going to check if CUDA is available. Now, CUDA is basically the interface by which we allow our code to run on GPUs. And we want to run it on GPUs because GPUs are really, really, really fast at running matrix operations. Like back in the olden days when we didn't have GPUs to use it, it would take days to weeks to train simple networks on just a CPU, because doing matrix multiplication on those is a time-intensive process. But back around 2010, with the foundation of the AlexNet model, they were able to write code to write it on GPUs, and suddenly training went from a thing that takes forever to a instant snap. And so that's what's used to train everything out. That's why you can't find NVIDIA GPUs anymore, why they're like always being scraped, scalped, and they're like expensive up the wazoo because of this. Because you can train neural networks on them. So for this, we're just going to check if CUDA is available, which means we have a GPU. Yours should say true. And then we're just going to define our device that we will be using for our model as either CUDA 0, if we can use CUDA. Otherwise, we have our CPU. And it should be CUDA. If it's not CUDA, please let me know. No? Everyone good? Great. So tonight, the data set we are going to be working with is the MNIST data set. And the MNIST data set is a very foundational deep learning library, deep learning data set for doing digit classification, like handwritten digits. Very simple, basically just a 28 by 28 image that we're going to pass into the network, and we're going to try to predict what output is, what digit is inside that image. And so tonight we're going to do a very simple network with that. And that's the one. Let me scroll to my complete notebook. So for that, we're going to need to grab our data. And so for that, we're going to do our training data of datasets.mnist. We're going to set the root folder we're going to save to as data. This is going to be our training set, so we need train true. We need to download the data from the internet, so that's going to be download equals true. Then similarly, for our testing set, we're going to do mnist is root equals data. Train is equal to false, because we're doing our testing, not our training. Then download is equal to true. A small extra bit we need to do is to just define a transformation. And so this is basically just going to be some wrapper code to make it easier to feed our data into the model. And for that, we're just going to do to tensor. And this just converts the model from like the NumPy format into the PyTorch format, which is just easier for the model to work with. It can do NumPy format, but it then has to convert that data, which is very inconvenient. So just to add that in, we're going to do transform equals transformation. Transform equals transformation. And then you just have to do a rinse cell. And then you should see it all downloading the data. It's going to take a little bit. Let me know if any of you are not seeing this. Also on mine, if no one's seeing this. Yeah, there's extra data from this URL that's not going to download. Everything we're going to be downloading is fine. So it should complete, and then you should see the little green check mark, meaning we have our data. And you should be able to see it here. Like if you go to the tab here and press the folder icon, you should be able to see your data, MNIST, raw, And then all of our input, our training and our testing data. Yeah,
For using data, like, what's that mean?
just the data folder we're saving to. That's basically just this folder.
So the quotes data is like the name of the folder?
Yeah, that's just the name we're gonna save it to. You can name it to anything. You can name it to pineapple if you wanted. It's just the folder you're gonna use. Yep. So we should probably take a peek at what our data looks like. So this is basically just some simple code for checking what our data looks like. We're just wrapping it basically around a simple data loader, which lets us grab our data. And then we're gonna just show some examples. So this is kind of what our data is looking like. It's basically just very simple images, like very small images of a number along with a ground truth label with what is inside of the image. Does that make sense? Very simple data. So we're going to take this. So the way our model is going to work then is that we are going to take in our image. We're going to pass this in to some hidden layers. And then we're going to go to 10 outputs. We're going to be like 0, 1, 2, ... 9, which will be basically the prediction that this image is each of the digits. So like, it's going to be like a 2% chance it's 0, a 15% chance it's 1, and like a 7% chance it's 2, and like a 3% chance. Does that make sense? Yeah, so that's going to be our basic architecture. We're going to feed in the image, pass through a bunch of hidden layers, and have 10 outputs of what it could be. And so for that, we're going to design our model in PyTorch. And so here, we're going to have like a very basic neural network class. Now we're going to just do like our neural network modeling, and we're going to define our model and our forwards. So for that, we're going to do so we're going to say self.layers equal to neural network.sequential. And so we're going to do that neural.linear. So we're going to actually first do neural network.flatten. And so neural network.flatten is like what Alejandro was describing before, in that since we're passing in an image that's basically just a bunch of pixels in a grid, we're basically just going to flatten those out into a giant list of pixels. And so that's going to be our actual input to the model, is all the pixels in our network.
So do you call like a flattened matrix?
Yeah, this is just a vector. We're going to do neural network.flatten. And then we're going to do neural network.linear. And so that's going to be our input and then our output. So our images are 28 by 28 pixels. So our input is going to be 28 by 28. And so then we're going to have some number of output. So we're going to have some output neurons to our hidden layer. Well, we're going to say this is like 5 to 12. This is hidden layer 1.
You pick 5 balls.
Arbitrary. But arbitrary, and I wrote this code up previously. That's one of the things about designing neural networks, is that finding what number of neurons you need is a difficult task that takes time to figure out. Because you never know how many you need. There's actually an entire field called neural architecture search, which is literally all about trying to search for the best architecture for your problem, like finding an automated searching system. So that's our first hidden layer. I'm going to do f.relu. I think this should work. We should probably cut that one. And neural network.linear. Let's do a second hidden layer. In layer 2. I think instead of f.relu, we should instead, sorry for that. So we should do instead nn.residue. This is a better way of doing it. That's our non-linear activation. Then there is our second prelude. Our non-linear activation. And then we will just set it as our output of nn dot linear of R512 to our output. So this is our output. Simple architecture, right? And then all we have to do for our forward, and we're going to do return dot self dot layers x. That's our network. Congratulations, you've written a neural network. It's crazy. And all we have to do is just run, and all you have to do is press play, and it should instantly run. Everyone good? Good. So then we should just have to create a model. We just do neural network. We then send that over to our GPU, and we can double check everything's working. And it is. And so we basically what this shows is that we have our neural network of a bunch of layers in sequence. We're going to flatten our image out. Then we have our linear layer of 784 input nodes, and then 512 hidden nodes at our hidden layer, along with bias values, which we then, once we go through our linear, we're going to wrap that around our ReLU function. Then we're passing that through another hidden layer of 512 to 512 with bias. And then we're pass that out from 512 to our net. And to just draw out what that looks like. So you guys can have like a visual example. That's our image. To first thing, flatten. X1, X2, dot, to X784. So this is flattened. Then we pass that through to our in layer 1. This is 512. In layer 1. Then we pass that to another hidden layer. Layer 2, 512. And then we pass that through to our final layer of 10, and this is output. A very simple model with just 2 layers and then our output. Yeah.
The second hidden layer, like the number of input features, does it have to be the same as
Yes.
the number of output features from the previous layer?
Yes. The input into the input of the next layer has to match the output of the previous layer.
And then the size of that layer is just output.
Yeah.
And that's the one that we're about to change.
Yes. So you can change this value. You can change this value to be whatever you want, but this value will always depend on the value of the previous layer. Yeah.
How do you get the like little console to show up so I can like when you click return self layers, like how it showed like all the like networks, was that something else or?
Oh, no, that's me down here. That's me just printing out my model.
Okay.
Yeah, I created an object of my model and then I just printed it out. So great, we now have our model defined. You've now done half of the work. So now is where we set up the training process. So if you remember before, let's see if I can fancy this. Remember this? We're basically going to be doing this little bit of code.
Except for the terminating condition
Uh,
on the while loop.
yeah. Yeah, let me scroll back up. No, I didn't mean to put that. So, yeah, so we're going to be working on this little bit of, there we go, this little bit of code next. Can I just, there we go. You all can still see this, right?
Yeah.
Or do I need to zoom in? You good? Okay, good. So we're going to basically write what we had written here. So we're gonna first have to compute our input. So we're gonna do, but first, we actually have to send our models to our GPU. We're gonna do x.x2 equals to device, and then y is equal to y.to device. And when this is just sending our data over to our GPU. And then we're gonna do prediction is equal to model x. And then loss is our loss function prediction y. Right? These first two steps. Then for back propagation, we're not going to do our optimizer dot zero grad. Then our loss dot backward. Then our optimizer dot step. Simple enough, right? Congratulations, that's the code for our training loop. You take this for a second.
Oh, yeah, so. I was getting like an error on, like trying to print out the model.
Oh. What is your error saying? Sorry, everyone.
Says this, but.
You made a typo, scroll back up. Scroll down. Oh, you made a typo, scroll up, scroll to your network. We only need one reason, you don't need the rest, yeah, you should get. So, okay, so that's basically the wrapper code. So that's just our basic wrapping of that. Similarly, for our test code, so we need to evaluate our model as well. We're gonna do x equals. Definitely x equals x dot two device, then y equals dot y dot two device, which again is just sending over to our GPU. And then unlike the training loop where we're gonna calculate the gradients and all that, we're just gonna do our predictions of our model. And we're gonna just add our test loss in of our loss function of our predictions and our y, and then we just grab item so we can actually grab the values themselves. And then we're just going to add the number of values we got correct by doing prediction at argmax, which is just basically the maximum value of the output, which is just which one is most likely. Then we just check if that's actually the correct match. And we just do type dot torch dot float. And then cast things to be a float. And we add things, then we sum all the correct answers together. Then one. Item is basically just basically item is a function that grabs the PyTorch stuff out of the GPU into the CPU for us to use.
Okay.
Yeah.
You and puts it into the CPU.
Yeah, it's not, that's actually not correct. I shouldn't say that. It's not grounding from the GPU to the CPU. It's basically just extracting out the values out of the tensor itself.
Okay.
Because all the values are wrapped in tensors, which is like, I don't want to get into what a tensor is right now,
Yeah.
but basically we're just grabbing the value, the item value itself inside the tensor.
And then it returns it to what, like a normal variable?
Yeah.
Okay. Tensors are just like multi-dimensional arrays, right?
Yeah. And then to also set up our test loss, we can do test loss is equal to 0. And our correct is equal to 0. And then we should just be able to run these both. And they should work. Yep. And so now we get to setting up our training parameters. So if you remember, there were a couple things we need to set. First is the epochs, which is the number of times we're going to loop through our that training cycle for the gradients and all that. To convert, for tonight, we're just going to manually set it to 20. For our learning rate, which is how much we adjust, let's set that to 1e-3. And then for our batch size, which is the number of samples we're actually going to be using to calculate our gradients, because our training set has 60,000 examples in it. And 60,000 examples takes forever to calculate. So instead, we're going to do 64 examples. And then after, so then we're not gonna run that cell. And then we have to define our loss function and our optimizer. Loss function is how we measure the performance of our model, and then optimizer is how we control us adjusting the gradients adaptively. Like, we're not just saying multiply by the loss function, we're like saying adjust the loss function based on our training. So for that, for the loss, we're going to use cross entropy loss, but we're classifying digits tonight. And then for our optimizer, we're going to do optim.sgd. And then we're going to do model.parameters. And model.parameters is all of our model weights, like that W we saw earlier, that's what model.parameters does. Then LR is going to be our learning rate. Then we just run this as well. Very cool. Just zoom in a little bit more. And so, everyone good on this so far?
Yeah.
Great. So now for our data loaders. Now, next we're gonna do data. Data loaders are basically PyTorch's library for like making it easy to load and batch up your data. Because you need some way of like randomly mixing up your data and sending out the batches. So that's what data loader is for. So then we're just going to do data loader. For the training, we're going to do our training data. Our batch size is our batch size. We're going to set it shuffle is equal to true, so that every time we grab a batch, it's a new random batch. And then num workers, which is the number of CPUs we'll use on our end to grab data, is 2, because otherwise it takes forever. Then we're going to do similarly data loader for our testing data, which is test data. Batch size is equal to batch size. Shuffle is equal to true, and then num workers is equal to do. And you should be able to just run this out. And now we should be able to train everything. So let's just write our very simple training. We already wrote the functions earlier for doing the training evaluation and the testing evaluation. So we're not going to call those. So we're going to do for epic in epics. So in range epics, print epic plus 1. And cut in, and then we're going to do printing. We're going to do train loop of our train data loader of our model, which is the model we defined earlier, our loss function, then our optimizer. Then similarly, once we did one iteration of our training, we'll then do one iteration of our testing. And that's going to be test data loader, model loss function, and then let's just print done. Okay, already. Now we begin training. Now I'm going to teach you a secret about training neural networks. They take frickin' forever. I had made a mistake somewhere. Sorry, 1 second. Sorry, everyone. We need to stop for a second. I made a small mistake. So if y'all could scroll back with me up to the test loop we did here. Sorry about that. I forgot to do a small writing of code that we need to do. We need to do test loss divided by num batches, and then correct that equals to size. We just need to do this because this defines this just lets us define, like, this lets us average out our test loss in the number of correct. This is our accuracy and our average error. And then I just forgot to average it. That was my bad. Apologies, everyone. So just run that cell again, and then I will scroll back down, and now we should be able to actually train. And now our loss values that we should be printing out should look more normal. Yeah, see, now we're getting like normal, we're getting normal accuracy and normal loss. And so we're just going to let this run for a bit. This, what I was trying to say earlier, is downside of neural network training. It takes forever. For tonight, it only should take like a couple minutes. But we're going to be training for 20 epics, so we kind of have to just let it iterate.
Is this stuff like the 64 over 60,000?
So this is the number of training samples we have in our data. We have 60,000 examples we're training on every epic.
Are we we aren't supposed to be getting 100% every time, right?
Oh, no way.
I don't think the model is perfect.
No.
No, it should start like poorly and then you get better, increase it.
Guessing it's
Let me scroll back down.
might be because the accuracy formula is incorrect. So it's supposed to.
Oh, you're dividing number of by number
Yeah,
of
that's
it should be by size.
Size, yeah. I was gonna say, I don't think the model's perfect that quick.
Yeah,
So Nick, is there a way to determine what's the optimal number of epics?
no, that's one of the reasons why people do early stopping, is because you don't know what the number of epics is, correct? You either just have to try a bunch. So the usual way they do it is that they train it for a little bit, see if everything's good, and then if it's good, they train a little bit more, and then a little bit more, and then a little bit more. Or people just train, or they just randomly test the number of epics and then train everything. But early stopping is usually what's used though, is like they'll just set a massive number, and then they'll have a validation set, and then they'll just train until the validation set's triggered on.
Okay, got it. Yeah, that makes sense.
Yeah.
That seems fair.
Yeah.
For every epic, we're using the same data, right?
Yes, we're doing the same data, but we're shuffling it around.
So like the 64 and like epic 17 would be different from the first 64 and like epic 18.
Yeah.
Yeah, exactly.
So the accuracy is based off of like the data we aren't adjusting our weights on.
Exactly.
Okay.
That's our testing data. Because it's a data we've never seen before to the model. Like the model has never like ever used it for learning, so it's completely new to it.
Okay.
And so we should be wrapping up training right about now. 89.9%, that's a really good model. That's a B plus. And we started at, scroll.
Let's go.
And we started at 74.
Oh, wow. I started like 45.
Yeah, technically you start at 45. I just did a printing mistake on mine. So like I actually started at 40 and now we're at 90. That's awesome, isn't it?
Yeah.
So that's the trick about training, is that you can basically watch as your model learns really well. And that's the whole point of your epics, is that you watch how well it's learning. And so we can now look at like a prediction of them. So this is just some basic code I wrote for just like taking some of the example data we have and then predicting out our model outputs. And then when we look at it,
So it thought that 5 is a 3.
it did think that 5 is a 3. That's why it's a 90% accuracy and not like 100%. But everything else, it seems to got right. Oh no, it thought both 5s were 3s.
Well, it's the same, like data, right? Because like 504, 192, 504, 192.
Oh yeah, I guess it is. I never noticed that. That's funny. What if I just run it again?
Yeah, no, I tried that. It's like part of it.
Whatever, doesn't matter. So yeah, so that's our data. So like it made a prediction of 5 and a 0. It did pretty well. Got 5 out of the 6 in the prediction, right? But pretty good, right?
Yeah.
What are y'all looking like? Is that similar, or are y'all doing better or worse?
My model's about to finish up. It says its accuracy is 91.2.
Hey, you did better.
Hey, I got the 5 right.
Yay, congratulations. Nice. So cool. So cool.
More training.
So now I wrote this little bit of like testing code here so that we can like try our own, so we can just write our own numbers in. So just run it,
Yeah, that's great.
and then we can just write our own numbers. What number do you all want me to write?
8.
8, all right.
Right.
Cool. and then
You
finish.
write a really bad 3.
And so,
Those fun.
yeah, I don't want to hold y'all to forever for this. I can promise the actual code in the Finish Notebook works. I know that my words don't seem believable when it's like clearly not working here, but. That's why we have Finish Notebooks, because Finish Notebooks do work. Do you all want me to keep trying to make this work with you all, guys? Continue. All right, I'll let y'all go. Thank y'all for coming tonight. I'm sorry I couldn't get the interactive example working. This always happened with code, like, it's always happened with interactive code, especially when you're writing in.
No worries. Thank you for the work out there.
Yeah, thank you.
Thank you so much.
Yeah, thank y'all for coming. I really appreciate it.